So now that we understand the underpinnings of typing, we want to build a fully functional type checker that can determine if a term belongs to some type. And let me show you how we'll do that. So we need a couple of preliminaries first. We have a function that determines type equality. So there's essentially two parts to this function, and I can actually show you this in the Coq proof solver. The first part that you see here matches T1 and T2, the two types were given, with two Boolean values. If they are of type bool, then we say that it's true and the types are equal. Then we try matching them with functional values. So this is a function that maps T11 onto T12 and T21 onto T22. So we just take the first term from each of these and we see if those types are equal recursively. And we also take the second term and determine if those types are equal. If both of those cases are true, then the functional types are also equal by definition. If both of those cases fail, then we just determine it to be false. So that's the basic equality. Now we can determine if this is in fact equality by determining if it is transitive and reflective, reflexive, as you can see here. So this is also done in the proof solver. So this is the proof for the fact that this relation is reflexive. We start by introducing type T, and then we make our inductive goal to be that this type relation is in fact true. For two types, if it's the same type, then it is true. So we can just make this true by reflexivity, and then we substitute in our inductive hypothesis on both sides. As you can see, our inductive hypothesis here, that if you have T1 and T1, that is true. If you have T2 and T2, that evaluates to true. So now we know that these basics, true equals true, is also true, and we can solve that by reflexivity. Alright, then we get into the proof for transitivity, which is a little more complicated. So let me show you what we do. We introduce T1, we perform induction on T1, we introduce T2, and also perform induction on that, and then we have inversion. So now we have this inductive hypothesis with two functions, one mapped onto the other. So now in the case that T1 is a Boolean, this can be reduced via reflexivity immediately because we know a concrete type that it is in fact Boolean. It becomes more difficult if it's a functional type. If it is, then we have to rewrite this via our initial inductive hypothesis. So we do that for both sides of the term. We can see we have our two inductive hypotheses here. Then we apply the inductive hypothesis, substituting in this value. So we now know that this is just true, and we know that the two first terms are equal in this case. We apply that also to the second term that we've generated. And then by substituting in our inductive hypothesis on both of them, we can prove this, that the transitive property is true. Our second set of preliminaries matches two potentially stuck types. So if either of the types is stuck, we declare that this is a failure. If neither of them is stuck, then we can continue onwards. And then the second preliminary just essentially makes it easier for us to read this. So if a type is not stuck, then we just return it. If a type is stuck, then we just call it a failure within our type checker. Alright, so this is the type checker itself. Let me go over some basic attributes of it, and I'll then show you the code running in Coq. So our base case, we check for stuck expressions if t is not stuck and resolved into a type, then we return it. If not, then it's considered a failure, and the type is in the end stuck. Our second case resolves mappings from one type to another via functions. Our third case compares two typed functions. It makes sure that the types match the input values of the function in the relation we already saw. So the first input of each function and the second input, or I guess the output of each function, match. Our next case is basic Boolean types. So, if it's true or if it's false, then its type is Boolean. And then the final case is decomposing if loops. So we make sure that this variable guard is a Boolean, and we make sure that the types T1 and T2 both match, so that the types can be resolved fully in the tree. All right, so let me show you running this. Oh, let me show this running in Gawk. Pull it up very quickly. All right, so I'll step through the first try before they cleaned up the notation, and then we can see here this is our full type checker with each one of the cases that I just described implemented within it. All right, play again from current slide. Swap presenter, and we're good. Okay, so this is the basic format of our type checker. If we put a term in here with a context, we can determine its type fully or determine if it's stuck. So this is a very limited type checker. It only checks a few terms. It has Booleans, it has type resolution, it has types in functions, and it can compare functions which have a given input and output type. It has if statements, and it can determine if a type is stuck. So a more robust type checker, such as you would implement for any modern language, I chose Java in particular because it's very strongly typed. So it would need to handle collection types, types in enumerations like lists or arrays. It would need to handle polymorphism, which is a pretty difficult task, as I'll discuss a little later in this presentation. It would need to handle typecasting, whether typecasting is possible, whether there's an implicit or an explicit cast for a given type. It would need to handle dynamic types, resolved only at runtime, which is sort of implicated with polymorphism. Like I said, implicitly typed variables, when you can use the keyword var in Java, and it'll infer the type for you. It needs to handle nullable types, which can technically have two types, one of whatever its original type is and one of null. Shallow/non-shallow types, when types contain other types, how does that work? Many other features. And so doing all of this in Coq would take quite a long time, but it is technically possible, as we've shown through our limited demonstration. I did do a little bit of research into polymorphic type checking because the field really interested me. So based on this paper that I read by Luca Cardelli, he discusses just basic polymorphic type checking based off of the research he's done and some academic contacts that he's discussed this with. So it uses generic variables which describe a type before it is fully resolved. It determines whether a variable is generic or non-generic, and whether it needs to resolve it at runtime or before runtime. This is difficult for recursive functions and for passing these variables in general, because non-generic variables should be passed as they are or passed by reference. But if you pass a generic variable by reference, it might get resolved into different types in different places and thus have a very unexpected behavior. So if you're interested in this, please look more at this paper by Luca Cardelli. It was really interesting and it helped me a lot. I think that's all I have for today. Thank you for listening, and thank you to Professor Novak for teaching this class.